Hey there, and welcome to The Explainer. Today, we're going to explore the incredibly fascinating languages of geometry. We'll look at exactly how we map our world, how we navigate space, and how simply shifting our mathematical perspective can completely change our view of reality. Let's get right to it. Okay, let's dive into this. I want you to think for a second about how you communicate location in your everyday life. Like, if you're trying to tell a friend exactly where you are in a crowded park, or where a specific coffee shop is located, how do you do it? Do you use streets and avenues? Do you just point and say, hey, it's over there? Describing exactly where a point exists in space is a fundamental human need. But mathematically, how we choose to answer that question actually makes all the difference. And that brings us to our core concept. A coordinate system is, well, it's basically the mathematical language we use to describe the exact location of a point in space. It gives us a totally standardized way to say X marks the spot. But here's the thing. Just like human languages, there isn't only one way to speak. Today we're going to look at two distinct mathematical languages that describe the exact same reality, but they use entirely different vocabularies to pull it off.
Section 1. Cartesian, the grid system.
Now, if you've ever looked at a standard graph in school, you've seen the Cartesian system. It breaks down any location into two perpendicular components. On side A, we have the horizontal distance, that's your x-axis. And on side B, we have the vertical distance, the y-axis. It's rigid, it's boxy, and it relies entirely on moving left to right and up and down.
The entire Cartesian system is built from the ground up to answer one very specific, very intuitive question. How far along each axis? It really doesn't care about angles, it doesn't care about taking shortcuts. It just wants to know exactly how many steps you need to take horizontally and how many steps you need to take vertically to reach your destination.
Let's actually walk through this visually. Say we want to plot the Cartesian point 3, 4. We move exactly 3 units to the right along the horizontal x-axis, right? And then from there, we go 4 units straight up the vertical y-axis. The opposite corner of that resulting rectangular space, boom, that's our point.
Because this grid system is so incredibly structured and predictable, it is absolutely ideal for things like engineering, working with complex matrices, linear algebra, and computer graphics. It's also completely foundational for global navigation satellite systems, or GNSS, specifically when we're dealing with formats like ENU and ECEF coordinates. Honestly, whenever you need to build a digital world or engineer a physical bridge, the grid system shines perfectly.
Section 2. Polar, the radar approach. So, unlike the Cartesian system, polar coordinates just completely throw away the idea of horizontal and vertical axes. Gone. Instead, they rely on side A, an outward distance from the center, which we call r for radius, and side B, a specific angle of direction, which we call theta. So, there's no more left, right, up, or down. It's all about aiming and shooting outward.
Now, what's really interesting here is how this fundamentally shifts our core question. We're no longer asking how far along an axis. Not at all. The polar system asks, how far away and in what direction? Just think about standing in the middle of a massive open field. You wouldn't tell someone to walk 10 paces north and 5 paces east. You just point and say, go that way for 50 feet. That is the intuitive power of the polar system.
Let's plot a point using this new language. To find the polar coordinate 553 degrees, step 1, we stand at the center point and rotate to exactly 53 degrees. Then, step 2, facing that exact direction, we just walk straight outward exactly 5 units. It's this sweeping, rotational motion followed by a direct, straight line.
And because this system models how things actually move through open space, the environments where polar coordinates thrive are very different from the Cartesian grid. This perspective is absolutely ideal for maritime and flight navigation, radar screens, the orbital motion of planets and satellites, understanding waves and rotations, and determining azimuth and elevation in GNSS. Anywhere that involves spinning, orbiting, or radiating outward, thinking in terms of radius and angle is just far more natural. This brilliantly illustrates a real-world physical analogy straight from our source material. The Cartesian approach is basically like navigating city blocks. Walk 3 meters east, then turn and walk 4 meters north. But the polar approach, that's like a radar operator on a ship. Target is 5 meters away at a 53-degree angle. City blocks versus open water. They're two entirely different ways to think about moving through the world.
Section 3. Bridging the two worlds.
But here's where things get truly fascinating. So, the crucial point is this. They describe the exact same point, No way around it. The Cartesian coordinate of 3, 4 lands you in the exact same physical spot as the polar coordinate of 553 degrees. The location itself literally never moved. The geometry didn't change at all. What changed was simply the mathematical lens we used to view it.
And because they describe the exact same reality, we can actually translate between the two languages using conversion formulas. You can think of these equations as your own personal mathematical decoder ring. If you have a polar point and want to find the Cartesian grid, you just use a bit of trigonometry. The horizontal x part is just the radius, multiplied by the cosine of the angle. The vertical y part is the radius multiplied by the sine of the angle. Simply put, cosine handles the horizontal and sine handles the vertical. It's an elegant, perfect translation.
And, of course, we can translate it in reverse just as easily. To go from a Cartesian grid point back to polar radar coordinates, we calculate the distance r using our old friend the Pythagorean theorem, so the square root of x squared plus y squared. For the angle, theta, we use the inverse tangent of y divided by x. Now don't let the math intimidate you here. The formulas are simply the sturdy bridge that connects the city grid right to the radar screen.
Section 4. Navigating the Real World.
So, we've explored the theory and the math behind these two perspectives. Let's ground this all into tangible reality. Take Global Navigation Satellite Systems, or GNSS. This is literally the GPS technology living in your pocket right now. And it doesn't pick just one coordinate system. In order to function, modern navigation tech fluidly switches between both Cartesian and polar languages, seamlessly utilizing whichever perspective is most efficient for the specific task at hand.
Let's move on and see how this builds into the systems that actually guide us around the globe. For global mapping, GNSS uses a Cartesian system called Earth-centered Earth-fixed, which is basically an XYZ grid for the whole planet. For local mapping, it uses another Cartesian grid called East-North-Up. But when measuring from the receiver in your hand to a satellite in space, it instantly switches to a polar-like system calculating azimuth, elevation, and range. It constantly classifies its data based on the precise geometry it needs in that exact millisecond.
And here is that real-world synthesis in action. When scientists and engineers calculate the highly complex orbits of satellites flying through space, they rely heavily on the structured Cartesian grid. But when a dish or an antenna on the ground actually needs to physically turn and point at that flying satellite, it switches to polar coordinates, aiming at a specific azimuth and elevation. Navigating space requires the grid, but pointing an antenna demands the radar approach.
Which brings us to our final thought. We've seen how Cartesian blocks and polar radii are really just two different lenses for the exact same geometry, but it leaves you wondering. If simply shifting our mathematical perspective completely changes the way we navigate space and solve physical problems, how else might adopting a new perspective change how you view the physical world around you? Definitely something to think about the next time you share your location. Thank you so much for joining me on this explainer, and keep looking at the world from new angles.